Hello, welcome to today's IEAGHG webinar on the recently published study reviewing the implications of unlikely but potential CO2 migration to the surface or shallow subsurface. My name is Nikki Clarke and I'm the Senior Geologist at IEAGHG, and I'm very pleased to welcome you to our webinar today. We'll be joined by Linda Stalker, Karsten Michael and Andrew Ross from CSIRO, who I'll introduce shortly. A quick note on the webinar procedures for today. As attendees, your mics will stay muted throughout. And if you have any questions for the speakers, please add it to the chat box and we'll address those either during the webinar or at the end during the Q&A session. Please also note that the webinar is being recorded and will be made available on our YouTube channel after the event. Unfortunately, we'll not be sharing our slides, but you will have access to the YouTube channel. I'll begin this webinar by presenting a short overview of IEAGHG, followed by a brief background and motivation to the study. I'll then be joined by my co-presenters, Linda Stalker, Karsten Michael and Andrew Ross, and we'll then have time for questions at the end. So please do type your questions into the chat box as we go along and I'll collate them at the end of the session. So the IEA Greenhouse Gas R&D Programme, IEAGHG, is an international programme that evaluates mitigation options for greenhouse gas reduction and has a programme focus on CO2 carbon capture and storage, CCS. Firstly, a short disclaimer slide that we show at the beginning of all our presentations. We're a collaborative international research programme founded under the International Energy Agency in 1991, but we're autonomous and our views do not necessarily represent the views of the IEA. IEAGHG are a members-based organisation, and thanks to their support, we can fund our research activities. We currently have 39 members, comprising countries, companies and organisations. Our members steer the direction of our research programme, and we have two new members, Ecopetrol from Colombia and Heritage Petroleum from Trinidad and Tobago. So IEAGHG helps facilitate knowledge sharing and connecting people through a number of pathways. And we do this in a number of ways. And our main activities comprise commissioning technical studies such as this one, with over 400 studies published via our website. We hold network workshops. You can find out about those via our newsletter or visit our events page for further details. We host the GHGT conference, which is coming to Australia in 2026, an international summer school, and we have external involvement with organisations such as the UNFCCC, IPCC, London Convention and ISO. Okay, so motivation for this study, reviewing the implications of unlikely but potential CO2 migration to surface or shallow subsurface. So an overview. The project was basically set up to review the past 15 to 20 years of progress in qualifying and quantifying the consequences and risk to environment and human health and to broader climate goals of CO2 migration to the surface or shallow subsurface from a geological storage site. It was specifically aimed at policymakers, project developers and regulators. So CO2 leakage from a geological storage site is considered highly unlikely from properly selected sites and potential impact is very small. However, it's still important to predict and understand the potential impacts and risks to the environment and to human health from a range of leak scenarios to design appropriate monitoring and mitigation to meet regulatory and societal expectations. And it's also important to balance the merits of CCS at a global scale to meet emissions targets and the potential risks at a local scale to these need to be evaluated. And as backdrop, we have a canon of around 20 years of academic and industrial research to glean from. So this study was conducted by CSIRO with the authors listed there and led by Linda Stalker. And the report was published for our members in January of this year and will be available for the public in July. And you can look at that on our publications library via our website. So moving on, I'm very pleased to welcome our presenters today of today's webinar. So we have Linda Stalker, who will be joining you shortly, who's a senior principal research scientist at CSIRO with active research in CCS covering geochemistry, monitoring, social license to operate and education. Dr. Karsten Michael is a principal research scientist at CSIRO, a hydrogeologist acting as technical advisor in CO2 geological storage. And Dr. Andrew Ross is the group leader of geochemistry, geosystems and geodata teams within Energy Resources Programme. So I will now hand over to Linda, who will take you on this journey further. and I'll see you for the Q&A. So.
And hopefully you will see slides in a second. Here, all right, of course I'm getting the wrong. Are you seeing the... Yep, all right, excellent.
Okay.
So excellent, thank you very much. And thanks to IEAGHG for the opportunity to both actually conduct the work and present the results as we've gone forward so far. I am just going to first of all explain who we are. For those of you who don't know, CSIRO is the Commonwealth Science and Industrial Research Organisation, and we are all going to fail Australian accents here today, but we are the Australian National Science Agency. We have one of the world's largest multidisciplinary science and technology organisations with over 5,000 staff across 58 sites. Both domestically and some internationally. And we have the great opportunity to use a lot of state-of-the-art national research infrastructure and apply that to the work we do. In the financial year 2021, we were able to deliver $7.6 billion of benefit to the nation. And our sort of superpower is the fact that we can reach through our organisation to a whole lot of different discipline areas. And so why are we doing this piece of work? Well, one of the reasons is that we have actually been doing CCS research for quite some time. Over 30 years, we've been involved in sort of every national CCS programme. We kicked off in the Geodis project. You can see Klaus Otto's name at the bottom of that list and various other worthies that have been around for a while. And we've been involved in the CO2 CRC project since it evolved out of the APCRC. We're both associated editors on international CCS journals. We're on technical advisory boards. We do commercial project reviews. We're involved with IPCC, ISO, various other things, and we do a whole bunch of actual work as well. We are also really lucky that we have some dedicated research infrastructure, some of which we'll be delighted to show you when you come to Perth in October 2026 to GHGT 18. So in terms of the talk today, the actual report itself would be quite tedious to go through from the front to the back. It's a lot of detailed information, a lot of review material. What we've done is we've actually used a framework with causal networks. And so what you see in that sort of flow chart is almost a graphical table of contents, and the report itself, you can actually click through each of those stages and follow the pieces of information you're actually interested in, rather than having to read the entire thing. You can actually sort of work your way through back and forth. So you may want to start at with the end in mind, or move yourself back. I'm seeing some notes saying that people can't see the slides. All right, some can. Okay, it's not me. Right, I will keep going. Oh no, lots of no slides. And lots of slides. Anyway. So we're going to go through some of this activity, and the other things that we want to explain is whether the general nature of the study versus the fact that you may use it for both actual physical sites and other places where this is a more generic activity, and then we'll go through a few conclusions. So bottom line up front really is it's all about, well, what happens if it leaks? It's the number one question that we all get asked about. What we're actually dealing with here is like looking at moderate to even major CO2 leaks, and we've defined through the study that leaks are unlikely to occur at well-characterized and well-operated, monitored and regulated storage sites. In the case of a leak, material impacts are unlikely and most mitigation tools are effective. And within the overall risk assessment framework of an environmental impact assessment, CO2 leakage from storage will rank relatively lowly compared to other mostly surface activities. So the causal networks, we're leaning on prior experiences and information and doing a whole lot of lit review, going from the driver, which is like we are trying to mitigate industrial emissions, the activity of the building of the facility, stressors like compromised well integrity, processes that might result from that, reaching towards an end point, which is a value pertaining to environmental and human health that people are really concerned and impacted, are worried about impacts. So we're mapping logical connections from the development through the activity to predict impact. And this framework has been work that Luke Peters has been developing over a number of years here at CSIRO. So I think I've jumped about 4 slides all of a sudden, sorry. We're all having problems. So here's an example of some of the causal network materials that we've got. So this is one example that Karsten's been working with partners in Geoscience Australia and Department of Water, trying to actually use that causal network pathway to try and understand what the impacts and risks might be. And what I'm going to show you is what the difference is between actually doing one for a specific location or project versus the global version that we have done for this generic study. And so you start to realize that we are dealing with quite a complicated situation where you're looking at a lot of resource development, and then there's a whole series of different activities that could compromise the situation. You can see that in the case of the Beetaloo subbasin in the Northern Territory, this study on geological and bioregional assessment is highly complicated. What it does do is those descriptions are really the literature review material for that specific location. We can then look at mapping and using GIS information to show where some of those impacts could be and how you might monitor and mitigate against them. And then you can actually start to sort of look at evaluations and the reference material. By contrast, what we've provided is really a PDF which you can navigate through to get to a more global scenario where you can start to sort of use that information. You can see where we've put all of the different literature reviews together, and then you can see where we've done the assessments, where we've gone, is it material? Can it be mitigated? And so forth, using the 20 plus years of the canon in this sort of area, and work our way through. And so you can jump through one particular avenue of information that you may find of interest, because this is designed very much for people who are not like deep researchers in CCS, but also for regulators as well as other people who may see a project coming their way. So with that, I'm going to hand over now to Karsten, and he's going to take you through the next part of the work.
Thanks, Linda. I hope I have. Is that the, because I see there's a note slides on that side, is that the presentation screen that we are sharing? Okay, right. Anyways, okay, so I'll be really looking and going through some of the pathways that are presented in the report. And this is just one of many block diagrams that is actually looking at the various impacts of leakage. But in this example, we'll be really concentrating or only looking at the environmental impact. So contamination of potable or usable groundwater, atmospheric emissions, and then also environmental impacts on the marine environment. You have seen this before, and this is basically, like Linda was saying, the graphic table of contents for the report. We can't go through everything, so I will go through a couple of pathways. One going from compromised well integrity, leakage into shallow aquifers, and then looking at the impacts on usable water. And then afterwards, Andrew will talk about the same pathways, but really going from environmental impacts offshore in the marine environment. And you can already see, like Linda was saying, this is a very general, high-level way to look at these impacts, and a lot of these things would make more sense if you look at them in geographical context. So there's a lot of generalization going on in here. Like Linda was saying, when you're clicking on these boxes, that's where most of the information in literature review sits, and then the arrows, they are actually the impact assessment, and they usually just contain one table with these questions. Is it possible? Is it material? And can it be mitigated? So starting with the compromised well integrity, we're using that example largely because when we're talking about leakage, we think that's probably the most likely way to actually for leakage to occur. But I should also say this on the left-hand side, you see the various well option that industry is using. So there's a large history of drilling wells and using wells partly even for disposing worse materials than CO2 storage. So that means our technology when it comes to well design based on other solutions, but then applied to CO2 is really well developed. We can still have compromised well integrity, and this largely refers to old and abandoned wells, and you see this relatively famous graphic from Gaster et al. So various ways for CO2 leaking through a well, either through the cement or even into the borehole through well plugs. But again, so even if you have leakage along these wells and going upwards, there are still various wells for the CO2 to escape into secondary containers and very buffering opportunities all up the well. So the likelihood that something like a major leak is actually occurring all the way up to the surface, even with badly abandoned wells, is relatively low. This slide I'm only showing, well, first of all, I'm really into gaseous, but these are basically cold water gaseous, CO2 gaseous. And the main reason why I'm showing this slide is really, well, what would really bad well leakage, what would that look like? So you're getting these gaseous, but then also all of these gaseous, they're usually in, well, they're always natural CO2 accumulation and a well being drilled into them. But you can see all of them have people standing right next to them. So when it actually comes to the hazards associated with like a relatively substantial well leak, they are relatively low and, at least in this case, is not of much concern. And so for this study, and like at least in the part, I think researchers have been struggling with actually looking at leakage rates, not only from wells, but also natural. So this recent publications from Daniels et al. We thought is a really helpful way actually to present the leakage, looking at the various categories from seep to a major leak, but then also looking at the likelihood. Obviously, there are some caveats to that as well. The study was largely done for the North Sea, and it's based on literature data and experience, and largely from the oil and gas industry. And you can basically argue whether the risk profile for CO2 injection well, where you're slowly increasing the pressure, is different from oil or gas production, where you're actually drilling into a pressurized reservoir. But you can see here the leakage rate from a seep. Some words to it. I mean, the really low ones are probably easily dispersed and absorbed, and unlikely that you need to remediate them. Similar with the minor leaks, but in this case, you can usually that can be easily addressed by existing well intervention and by either replacing components or placing plugs. When it comes to moderate leaks, so we're talking about 52,000 tons per day, we are talking about CO2 concentrations that might actually be dangerous to people working on it and the rates. So in this case, yeah, you might still be able to use temporary plugging techniques, but if the leak cannot be stopped or reduced, then an emergency relief may be required. And the major leak is just an extension of that, but in this case, it might be really difficult to repair, and you definitely need an emergency relief well. So looking at this in the graph and the various examples, and again, this come from the Daniels paper and some other literature. The cold water geysers that I just showed, they would looking at the leakage rate, they would be actually falling in the seep or minor leakage rates, and then only really active well blowouts, basically wells drilled into a pressurized reservoir, would really fall into this moderate to major leakage rate. And just for comparison, to put these rates into perspective, a car basically that would have like approximately 4.5 tons per year emissions would fall in the seep, just to put these numbers in perspective. And then what Daniels et al. Did as well, and again based on other literature, some of the more pertinent literature or references down here, is actually also looked at the likelihood of occurrence. So basically, you see the colors here again, the likelihood of a seep being about 1 in 10, then going to major leaks. And again, this is all based on petroleum, or largely based on a petroleum experience. But it also tells, so basically the chance of having a major leak is about 1 in 100,000 or 1 in a million. So if you're taking the example, for example, for the petroleum and gas industry, so an event horizon type incident, that would be a 1 in a million incident. So again, these numbers, I think, yeah, you would have to take them a little bit with a grain of salt, but at least it gives you a little bit of an idea what the probabilities are. And obviously, we don't really have any examples of CO2 leakage from industrial projects. This would need to be tested, and it's probably more on the conservative side. And just in comparison, because I'm not really talking this talk about geological leakage, you can look at similar probabilities for geological leakage from saline aquifers and depleted fields. The only point here is that you probably will never reach a major leak, just because, I mean, that would require a fault that you would have detected in your site characterization. So very, very unlikely. And then again, geological leakage from saline aquifers maybe a little bit more likely, because you don't have as much information as depleted field storage, where you pretty much know your geology, and yeah, the likelihood of having a leak is definitely less. And this brings us to the assessment, and I'm just going back to the table. So this is wirklich looking at the compromised well integrity. Will carbon geological storage cause compromised well integrity? And so if you're looking in this table, so if you don't want to read all the background information in the report, you can just go directly to the assessment. And so basically, this assessment is really simple. The key questions here, first of all, is it possible? And then, yeah, obviously, yes, it is possible. And you have some examples from EOR projects where you get some CO2 leaking from wells and petroleum wells. General, is it material? So this one is a little bit more tricky. I mean, we say yes, it can be, but it's probably very, very unlikely, because you're really looking at an inadequately completed well or well blowout. And again, you can look at the probabilities from Daniels. Can it be monitored? That's the nice thing about wells as opposed to geological storage, because they are point sources, so they are relatively easy to monitor. And you can look at some aspects here, microseismic events, and you can also look at wellhead injection pressures that need to stay below the fracture pressure of the reservoir or reactivation pressure. So yeah, this is definitely the advantage of wells. Can it be mitigated? Again, as opposed to geological storage, where you don't necessarily where the leak is. In the case of the well, you know where the well is, and from the petroleum industry, you have various ways and experience to properly mitigate it. And then mitigated, this is more like constructing the proper well, whereas remediation, sorry, I was that's really going back if it already happened. And again, yeah, we have that ability exist. So the summary really is, yeah, it's possible. It can be material, like in very few cases, but it can also be mitigated. And so that brings us then, so while it's possible, so what is really the impact on the various processes? And we are specifically looking here into CO2 leakage into shallow aquifers. And I mean, this has been discussed in the literature, like through various literature reviews and reviews of reviews. So you basically have the leakage or migration of CO2 beyond the plume, potentially impacting aquifers, especially their updipping beyond your storage reservoir, and then really the updip migration either through faults or through the wells. And again, the chemical processes are really well known. So basically you have impacts from the CO2 itself, changing the acidity, basically increasing the acidity, increasing salinity, but then this would trigger various reactions between CO2 dissolved in water and the rock. But at the same time, while you can have various elements, metals being released, you also have the natural attenuation. So not only because if you're going back outside the CO2 plume, a lot of these processes would be reversed, but then you also have other scavenging reactions that actually might, if you have the release of arsenic, it might actually be taken up by another process. So this is now the assessment directly, and this is really comparing the leakage from geological features versus well integrity features. The same question as before: is it possible? Obviously, yeah, in both cases, it is. Is it material? And that brings us back to the Daniels paper. So no, in most cases, geological leakage won't be material because leakage rates are small, diffuse and patchy. You have the various multiple barriers in between the reservoir and the surface, and various buffering and dissolution of CO2 along the way. So basically, it's very unlikely that you will get a material leakage with respect to leakage into shallow groundwater. With wells, it's a little bit different. I mean, you would have the same processes, but the wells basically potentially form a direct pathway into the aquifer. So there, the risk of materiality is a little bit higher. Can it be monitored? Yeah, obviously in both cases, because groundwater monitoring is pretty standard around any industrial operation, including CO2 storage. And then, but when it comes to mitigation, it's really hard because I mean, you can't really change or or you can predict the geology, but if you oversee a certain leakage pathway, there's nothing really that you can do except for doing a better characterization. Where when it comes to wells, obviously you can probably complete your well and also make sure that you're operating it under the right pressures. Could it be remediated? Again, yeah, plugging up geological pathways. I mean, there's some literature talking about it, but that's very difficult, especially because it's very dispersed and it's not necessarily like really a located leak. Whereas it's different for well leakage because again, you can re-enter a well and fix the well. So in summary, will compromise subsurface or well entry result in an increase in CO2 in shallow aquifers. It's possible, but like for geological leakage pathways, it's not material. And for wells, while it can be material, it can be easily mitigated. And this is basically taking us to the last point. I mean, so while you have leakage into shallow aquifers, what is the impact, or would that have an impact on the usability of the water? Just a couple of notes. CO2 itself is not considered a contaminant, so it's not even necessarily required to measure CO2. So the only thing, and this is really as a secondary MCL or maximum contaminant level, it's really we're looking at pH. That's considered environmental impact assessment, which has a really wide range. So it's only if you're outside the 6.5 where you get this bitter metallic taste and corrosion, or at high pH, the soda taste. There's no real you need a lot of CO2 to actually raise the flag when it comes to environmental impacts. Obviously, the release of metals is a bigger problem, and you will have limits, groundwater limits for most of the metals. And this paper by Lyons et al. Goes through the various reactions that can either mobilize or scavenge these metals. And you can see here, so it's definitely possible, but looking at all the reviews and laboratory experiments and controlled release experiments, there's, in most cases, you don't get concentrations of any of these metals above environmental guidelines. So you need really special cases or already existing metal content in the water to actually raise it. So generally, it wouldn't be considered material or important. And so again, and this is the summary, and this again is the one-page table. Will CO2 leakage to shallow aquifers result in a decrease in usable water? Sure, it's possible, and very, very regional cases, and it's really location dependent. Is it material? Well, we would say no. Well, first of all, carbon dioxide itself is not considered a contaminant, like I said before. And looking at all the literature, and some of the literature is here, most studies conclude that the environmental impacts of CO2 leakage into groundwater plus the mobilization of trace elements is really, really low. And then it can it be monitored? Because we are so close to the surface, it's relatively easy to monitor. And also when it comes to mitigation and remediation, these technology exists in the groundwater space, and you're using it to treat water for use. So overall, we think, while CO2 leakage to shallow groundwater, or the leakage of CO2 into shallow groundwater is possible, in most cases, it won't be materially decrease the quality of your usable water. And that, I think, brings me to my end, and I hand over to Andy, looking at the marine impacts.
Okay, everybody, I think I have control now. I'm not sure, but I think I do. So yes, thanks, Karsten. And we're just going to go through another pathway here, looking at the processes and the endpoints for CO2 in the ocean and any endpoint marine biodiversity impact that may have. So let's just jump to the process. When I think most people on the line, if not all on the line, will understand that when CO2 dissolves in seawater, it forms carbonic acid, which changes its pH. Now, the pH of waters can be driven by several processes, such as total alkalinity inputs from freshwater input, mixing of higher salinity oceanic waters, including through upwelling, and then also biological activity, either through primary production or respiration of marine organisms, and of course, ocean acidification, which I'll touch on next. The pH in the waters can be impacted by seasonal and interannual variation, and variations in coastal waters is typically about 1 pH unit, but that variability can be as high as 1.6 pH units. So that's sort of the background for the pH changes in the marine environment. One of the changes that will occur over the lifetime of CCS projects that are located under the ocean and sea is ocean acidification. And ocean acidification is basically caused by the air-sea exchange equilibrium. As we're increasing our anthropogenic emissions in the atmosphere, the ocean is balancing those pH, that CO2 by absorbing CO2 into the ocean, and therefore we're getting increasing ocean acidification and decreasing pH. And that's an important consideration as we go forward. Another thing that we also know about CO2 and how it behaves in the marine environment is we have actually quite a lot of examples of marine CO2 seeps. The map on the left shows the confirmed and inferred shallow water hydrothermal vents, volcanic islands and underwater volcanoes that have CO2 seeps associated with them. And on the picture on the right is an example of a vent forming site in Volcano Island in Italy. And you can see the distributed nature of the CO2 bubbles within the water there. From those studies, we can understand how CO2 is released from the seabed, and it's released in the form of CO2 as a gaseous form and also CO2 saturated waters and brines. CO2 bubbles typically have spherical diameters of 5 to 100 mils, and the bubbles would divide or collapse as pressure diminishes as they rise up through the water column. As they rise, the CO2 will rapidly dissolve in the water from the bubbles, and the bubble plumes may not actually reach the sea surface, particularly in deeper waters. And so the Gross et al. Paper here was a study about one of these seeps and looking at the diameter of the bubbles as they made their way through the water column, the mole fraction, gas mole fraction changes, and also the actual fraction of initial CO2 in the gas phase as it moved up through the water column. So bubble plumes are readily detectable using acoustic methods such as single beam or multi-beam echo sounders, although they can be confounded by biological activity in the water column as well. So we've got quite a good handle on what happens to CO2 in the water. Another way of looking at the impact or the effect of CO2 leakage into the water column is through modelling. Where in this case we're using detection length scales, and I'll try to explain it a bit. And so on the graphs on the right, we've got a coastal Gippsland region of Victoria example. There have been other examples by Jerry Blackford and others for the North Sea, which I encourage you to look at his papers. And here what we do is we have a hypothetical release of CO2 between 5 tons and 50 tons per day within the model. And we look at the area experiencing a drop of pH of 0.01 units, the black dots, or 0.02 units, the open symbols. And the 0.01 is important because I'll change the number on you shortly. So keep that in mind. We look at the longshore direction and the cross-shore direction in terms of where the change in pH would occur. And you can see that even at very large, well, 50 ton per day volumes of CO2 being released into the marine environment, we're only getting very small pH unit changes over a wide area. Wider area, and at a release rate of say 5 to 10 tons a day, actually the area that is being affected by that very small pH change is very, very small. So let's try to put some of the information that we've been talking about together. So at the figure on the right, we've got, in our particular case, the normal variation in pH in our example. Then over the near future, we will have changes in ocean acidity due to ocean acidification, and that will, into the far future, increase. So effectively, we've got a range of pH change that's just associated with ocean acidification in the medium to long future. We've got other things that affect pH in the water column as well, such as eutrophication. That can have a much greater impact upon pH than the changes in ocean acidification. And then underneath in the red bars, we've actually got the changes in pH range that could affect marine biota, different types of marine biota. And you can see, for example, bivalve larvae development would already be impacted or affected by eutrophication, for example. At the very bottom here, we've got a 0.1 pH change associated with a 30 meter in longshore direction and 6 meter in cross-shore direction change due to 45 ton per day model leakage scenario. So what you can see is that 0.1 pH change is almost, well, it's overprinted by the natural variation within the marine environment. So it would be very hard to distinguish that pH change from a leak versus the changes occurring naturally within the marine environment at any one time. So just using the well example, so will compromised well integrity result in an increase in carbon dioxide in the ocean? Well, yes, of course it will do. And is it material? Well, yes, a compromised well can create a direct pathway for CO2 to enter the ocean, and that can lead to locally material change in partial pressure of CO2 in seawater, and it would likely express on the seafloor as a number of small seepages, and therefore dispersion and dilution would be enhanced. As demonstrated, even at relatively high rates, leakage would have an impact length scale where pH changes were over 0.1 pH units would be of them of meters to tens of meters maximum. Can it be monitored? Yes, there are many marine monitoring techniques and technologies that are available for leakage detection throughout the water column, of which there's many publications on that. Could it be mitigated? Yes. An increased CO2 concentration in the ocean due to compromised well integrity can be avoided and mitigated by ensuring adequate barriers in construction or between injector wells or existing and abandoned wells. And it could be, can it be remediated? Well, as Karsten said in the other section of the talk, mitigation remediation technologies are well established and could be implemented. So in summary, it's possible and it can be material, but it can be mitigated in the well example. So let's have a look at what the impact on marine biodiversity could be, and I've already alluded to what that could be already. So in the study, we looked at impacts on informal biodiversity, i.e. the biota that lives within the sediments, the impacts on the benthic communities, those faunal communities that live on the seabed, the impacts on planktonic organisms, and impacts on fish. And I'm just going to go straight to the end here and ask the question, will carbon dioxide leakage into the ocean result in a decrease in marine biodiversity? Well, it is possible because the CO2 leaking into the seawater will decrease pH, and that can increase microphytobenthos productivity and decrease faunal biomass and trophic diversity, as one example. Now, is it material? We don't feel it's material. Depending on the particular marine setting, small single well leaks will have impact length scales where the changes in pH will be detectable over the order of meters to tens of meters from the leakage point. And would likely to be expressed on the seafloor as a number of small seepages, and therefore dispersion dilution would be enhanced. Only prolonged leakage along numerous wells to poorly mixed waters might compromise long-term CO2 storage and may adversely affect the local marine ecosystem. Can it be monitored? Yes, absolutely, it can be monitored. There's ways of doing that, but from looking at the biota, but more importantly, looking at the physical chemistry. And could it be mitigated? No, once the CO2 leak has reached the water column and changed the pH, it's difficult to avoid or mitigate. However, could it be remediated? Well, yes, on cessation of any leakage, faunal assemblages in the literature have been shown to repopulate areas previously affected by CO2 leakage. So in summary, it's possible, but not material. So hopefully that gives you an impression of how the report's structured and how we go across each of the areas. And Karsten, I've now messed that up totally because I'm going to have to go back to marine biodiversity and go back some of the slides and bring us to the conclusion. So in summary and conclusion, material impacts are unlikely to occur at well-characterized, adequately operated, monitored and regulated storage sites because the CO2 by itself is not a contaminant. Improbably large leak volumes are required for material changes. However, multiple barriers and migration within intervening aquifers, as well as buffering, dissolution and residual saturation will retard migration to reduce volumes migrating out of primary containers to more superficial situations. Within the overall risk assessment framework of an environmental impact assessment, CO2 leakage from storage will rank relatively low compared with impacts from surface activities and impacts from other subsurface activities such as oil and gas production and gas storage. So that pretty much rounds out our presentation. Here are some of the key literature that we've used in both the presentation and in the report. I recommend that you go and find some of that literature. It's very useful. And without further ado, thank you, and we'll open the floor to questions.
Thank you so
one
much.
More.
Yeah, you can click on one more. It just goes to Q&A. So I think I can answer that one. Melissa's asked, do you address leakage from pipeline ruptures? So this study was really based on the storage site itself. We didn't deal with any of the infrastructure leading up to site, so we didn't do anything with pipeline, although it has been suggested that maybe transportation would be a separate study, Melissa. So that's something that we could certainly look at in the future. And well blowouts in the marine environment. I think the way that, if I'm not right, the way that the structure of the report is that sort of wells were dealt with in one chapter, and then it was kind of like you went through the system and you looked at sort of what were the material results were in that. Is that right?
Yeah, and maybe to the first question regarding the pipeline ruptures, that was sort of our point that we were trying to make. I mean, there are a lot of things when it comes to CO2 leakage at the surface. It might be just fugitive emissions, but also anything with transport or pipelines, any surface facility. The emissions or potential leakage from these facilities, the risk is a lot higher than leakage from the subsurface reservoir. I guess that's one of the points, and I think that's important to consider by regulators when it comes to environmental impact assessments. And yeah, with the wells, yeah, we haven't specifically looked at well blowouts in the marine environment. But most of them, if it's a blowout, it will come up to the surface anyways, right? So it would bypass the water column unless it's completed at the seafloor, I guess.
I think it is worth talking about the blowout situation, because I think there's maybe a different way of thinking about well blowouts in an oil and gas context versus a CCS context. In a CCS context, you're going to be, if you're storing in saline aquifers, you're going to be drilling into an aquifer, and there is just water in the aquifer, salty water, but you might encounter overpressured water, but that's it. In a depleted reservoir sense, you're also going to have a depleted reservoir. You know exactly what the pressure is. So the likelihood of a well blowout with CO2, I think, is exceedingly low, because it's not a case of drilling into a reservoir that has high pressure gas in it. That's not happening. So it's quite a different scenario.
And I think the other thing is, in terms of pipeline activities, if you understand the way in which they're actually configured, and you look at some of the incidents that have happened in the US, within minutes, a lot of these pipelines are shut down because they're valving across the whole of the pipelines for the infrastructure and the operation. So I think there was one of the ones a few years back that I think the whole pipeline was shut down in about 4 to 9 minutes. So you're really restricted in the amount of blowout that you actually have as well from a pipeline accident. I think that was someone drove into it or something like that. So they're not the sort of things that you might expect to be the cause of some of these incidents, and there are a lot of operational mitigants that are available to the operators.
Yeah, and I think, and we haven't talked about the leakage to the atmosphere and atmospheric impacts or CO2 in the air. But so even these pipeline ruptures, it's not like methane where you have explosion risk. It's the CO2, and again, you need quite a lot of CO2 and pretty restricted environment, like being in a low-lying area for CO2 to accumulate to actually have any. Well, definitely in environmental impacts, but also impacts on human health. It's again pretty limited as long as you're in an open area and the CO2 doesn't accumulate.
Yeah, excellent. Good question. Okay, so another question from Joshua. Is there a major potential for using permanent downhole pressure temperature gauges for long-term monitoring of leakages?
Yeah, there is, and a lot of it is fiber optics. But Andy, maybe you want to see some more on that.
No, this having downhole monitoring is obviously a preferred approach. There's conventional downhole gauges that can be used, as well as more emergent technologies such as fiber optic sensing that can be used as well. Depends on the particular project and how the project needs to be monitored and what the key risks are as well, of course.
Perfect. And then we've got a question from Randy. Did you consider impacts of brine migration into freshwater resources?
No, we didn't, because I mean the scope of the study was specifically the impacts of CO2 leakage. So again, I mean, it's a little bit of a mixed bag, because obviously as CO2 changes the quality of the water or the pH, and you get remobilization, most of the transport of any other contaminants would be through the water phase and not through the CO2 phase. But in this case, no, we haven't specifically looked at it. But I mean, I have my personal opinion on it, because you have to, I mean, when you're looking at the pressure profile of an injection well, the pressures dissipate quite quickly away from the well. I think exponentially to the square of the radius. So actually having enough pressure to push a brine up a well, that potentially you have that in the direct vicinity of the injection well itself, but it's very, very unlikely in the far field of your injector.
Yeah. I think the other thing with that as well is we've obviously stated that the causal network that we put together here is very limited and and global in its kind of remit. But obviously if you were doing a project, you'd assess all risks associated with that project, not just the risk of CO2. And you'd end up with something, if you were doing causal network approach, you'd end up with something that, like Linda showed for the Beetaloo Basin, a very complex causal network. But obviously we were restricted here to CO2.
Excellent. Thank you so much. Is there any other questions in the chat? I think we did have a question earlier, which I think you addressed, Linda, which was sort of on, I guess, maybe looking at that risk of, or the challenge of trying to understand a risk profile from an oil and gas wells perspective we don't have enough data, do we, really, to know what those impacts are? And I guess most site characterizations are very cognizant of legacy well risk and trying to avoid any sites that really interact with those. So yeah, I don't know if you want to speak into that at all.
I think it's a real dilemma in terms of whether you want to go down a saline aquifer pathway where you're putting in absolutely pristine new wells where you have full control over what you've done, how you've done it, what materials you've used, versus accessing lots and lots of data from a depleted field that may have legacy wells. And I think people are looking at trying to do a really good evaluation of legacy wells, and they may well put you know, a line in the sand and say anything pre-date X we're not even going to address for these early projects. So, you know, it may come to pass that this is not as big a risk as we think, or it can be mitigated. But at the moment, for some of the early projects, I think, you know, you do want to pick your best plans, pick your best sites, reduce your risk to the absolute minimum to demonstrate that this is an effective way to do large-scale CO2 sort of mitigation.
Yeah, absolutely. Well, I want to thank you all for being here today, and thank you very much to our presenters. There's loads in the report, loads more to see. It is a global scale, but it does comprehensively and step by step go through these issues, and it's really easy to navigate. So hopefully it's very reasonable. So question from Melissa: how do we access the report? Let me know, Melissa. We'll make sure you get a copy of the report. Thank you to the presenters. That was great. Yeah, thank you so much, everybody, for joining.